Okay, then I can scroll up and down. That's easier. Okay, fine. So you see uh, photons that you can see, light emission from around the black hole, and there is this concept of a black hole shadow, which is if you take a trace of photons from around the black hole and look at its path to the observer, this is what one would see. Okay, and so that's on my front page. Now, next, I'd like to talk about black hole basics, some little bit about Kerr geometry, which is a spinning black hole, and observational aspects of black holes. A little bit about black hole electrodynamics, black hole formation, and I will also add to this the discovery of uh, the orbits around the central black hole and the singularity theorems for which the black hole Nobel Prize was given to the black hole in 2020, right, to Penrose and Andrea Ghez. Okay, so what are the four important forces that we know of in nature? One is the gravitational force, the other is a weak force, and the gravitational force mediates forces between masses. Weak force, of course, weak force and the electromagnetic force together form the electroweak interactions. And the electromagnetic force, of course, if the charges short out, that is, if you get positive and negative charge, then it can't, exert a force over longer distances. And then there's a stronger force which acts over nuclei. So if you look at the strength of the force and how it varies with distance, you can see that the electromagnetic force is much stronger. It goes over, and it can go over large distances provided it doesn't get screened out. The strong force has a cutoff, and the cutoff is at nuclear scales, and the weak force has a much stronger cutoff, right? So, and then gravity is the only long-range force. So in the universe, gravity will dominate over the entire stretch of the universe, right? So all the other forces get cut out. This is a very important thing which has effects that lead to mysterious objects like black holes. So black holes are formed out of, they can be formed at stellar scales. You can have neutron stars, white dwarfs, and black holes. This different sizes, 8 to 10 times the mass of the sun, or white dwarfs are 1 to 8 times the mass of the sun. And it can also have, black holes are much heavier. They can be from 8 to 60 solar masses. There are supermassive black holes, which are of millions to 10 to the power of 10 solar mass black holes. And they're formed at the time of galaxy formation itself. So they're formed when the galaxy forms, and there's a black hole at the center of almost every galaxy. So what is a black hole? It's a region that cannot communicate with the rest of the universe. Cannot communicate in the sense that you can't get any information from the inside of the black hole to the outside. And it represents a singularity in the Einstein's equation. And there are only three numbers that specify a black hole: the charge, the angular momentum, and the mass. So this uniquely specifies a black hole. Okay. What is the brief history of the idea? It goes back to Laplace, who said, okay, let me find out the escape velocity from a massive object and equate it to the speed of light. And then he found this radius. And this radius today is called the Schwarzschild radius, which came out as a consequence of solving the Einstein's equation exactly. So the Einstein conceptualized the theory of general relativity in 1915. And Karl Schwarzschild came up with this idea of a gravitational field around a point mass. In fact, he was a soldier in World War I when he derived this equation. And Chandrasekhar gave a physical reasoning for the existence of the black hole, and he said that the reason is that masses above a certain limit, stars above a certain mass can't protect itself from collapse. And so you can estimate that mass from these very simple arguments. If you take a ball of Fermi gas, and so if you estimate the Fermi energy, that is P of a relativistic gas, PFC per particle, PC is the energy per particle, then you can estimate the length scale. H by x would be the momentum. So x is written as n to the minus one third, which is the number density of the particles. And then from there you can estimate from the number density is the number of particles in a sphere of r cubed. You can find this, right? And then you can also write the energy per particle, gravitational energy per particle. That is gmmb by r. mb is the mass of one single particle. That's a baryon mass. And when you add the total energy, you see that both scale is 1 over r. So EF plus EG for a ball of Fermi particles having mass mb scales as 1 over r. And you see the number of particles to one third coming in here, and then mass coming here. So rest of the rest of the terms, rest of the part of the expression are just fundamental constants. So if you equate this to 0, so when the energy just becomes negative, or the system becomes bound, the gravity takes over the Fermi momentum. That is, the Fermi pressure is unable to hold itself against gravity. You can find that limit by putting it to 0. The R scales out, and then this gives you a number which is just telling you the total number of maximum number of baryons that can belong in that ball of gas, which cannot hold itself against gravity, at least by Fermi pressure. So what was used here is, you can just get h cross c by gmb square, and this turns out to be 2 times 10 to the power of 57. And this is the known as the Chandrasekhar mass. More exactly, it is 1.4 solar masses. So here, essentially, one is talking about Fermi pressure of electrons, and that is what is leading to this. Of course, when the star collapses further, then it can be supported by nuclear forces. So then the nuclear equation of state can come in. But this is only the Fermi pressure due to the presence of electrons which are acting as fermions. So what happens when it collapses? You can visualize this by solving the Einstein's equation. I'm not getting into those details, but what you end up doing is getting a Schwarzschild metric, or a metric which was derived by Schwarzschild to describe the exact solution of Einstein's field equation. Just tell you how the metric, that is the space-time around a non-rotating black hole behaves. It's a spherically symmetric metric. And then it has these ds squared is 1 minus 2m by r dt squared, and then there is this other term. So what's important is that if you look at the static part, that is, you just put dr, d theta, d phi to 0, then you can see that there is a relationship between proper time and the time of the local clock. So this dt signifies a local clock, and d tau is a proper time, which is like the time measured at infinity. So there's a relationship between the clock that is ticking at infinity and the local clock. As you can see, the time at infinity is clicking faster than the local clock. So that applies even to a gravitational redshift. What do you mean by gravitational redshift? So an emitted photon would then change its frequency from the emitted emitted value, by a factor given by this, the same argument. So time is changed to frequency, and then you can take a flip it over, and then you can see that you get 1 minus 2m by r em. So depending on where it's emitted, the photons will change its color. So here's an example. So let's say you are shooting X-ray photons. So at different distances, say this is a black hole which is a 3 kilometer diameter, and this is the Schwarzschild black hole of mass equal to the solar mass. So if you take the sun and collapse it and make a black hole, the size will be just 3 kilometers. Okay. So at 10 kilometers, if it's close to 10 kilometers, let's say you release an X-ray photon, then by the time it reaches 100 kilometers, it will be ultraviolet, and 10,000 kilometers will be visible wavelength. Suppose you shot off a visible photon, then it becomes infrared by the time you reach 100 kilometers, and at around 10 to the power of 4 kilometers, it becomes a radio photon. So the photons become redder, or they have longer wavelengths or lower frequencies compared to those that are emitted. And the time freezes for a distant observer watching something fall past the event horizon. All right. So what are the conclusions that one can make about compact objects? Suppose I draw this figure of density versus radius, right? So this is m over r cubed, and this is r, right? And for a black hole, you know that the radius of the black hole is gm by c squared. It's proportional to the mass. So when you write the density, it goes as 1 over m squared, right? M by r cubed goes as m by m cubed is 1 over m squared. So this slope is -2. So beyond a certain point, that is the higher density, moment you go to a higher density for the same size, you will turn into a black hole. The interesting thing that you will notice is that if you go to 10 to the 8 solar mass, if you go to density of water, let us say the density of water, the radius would be 10 to the power 13 or something like that. Yeah, 10 to the power 13, which corresponds to the Schwarzschild radius of a 10 to the 8 solar mass black hole. So you can see that various objects here are very far away from the black hole limit, and you can see that white dwarfs and neutron stars are closer than the other objects. So the moment you're closer to this line, then that's the death line. So objects will become a black hole collapse. So all the collapses will lead to black holes on the right hand side of the diagram. This is a cartoon actually drawn by George Gamow in one of his books about Chandrasekhar's discovery, and there was a paper by Chandrasekhar and Kothari where they actually plot the same thing of collapse, right? This is the radius and mass relationship, and just for fun he just wrote radius and mass in Tamil, right? Because Chandrasekhar was, George Gamow had a curious sense of humor. So this is the diagram of how the degenerate behavior, density behaves. So this is the radius and mass relationship for degenerate systems. So beyond a certain point, you can see that m times r cubed is constant. That is, if you increase m, the radius keeps shrinking. So that's when the mass, the mass takes over, the gravity takes over, and it becomes smaller. So that's beyond a certain point. Otherwise, they're just given by solid state forces up to this maximum. So this is an equation of state which is derived by Chandrasekhar and Kothari. And let's look at how photon trajectories behave. If you have a normal star, you'll find that the photon trajectory, just like on Earth, they travel in straight paths here. But if you're in front of a collapsing star, the light rays will bend because of gravity. It'll tend to bend. So you'll have one photon going straight, the others will just fall around like that. And if you're inside the black hole, the photons are trapped. Okay. Here's another example of a girl standing in front of the black hole, and she can see the back of her head because a photon from the back of her head can orbit around, and she can see it. Okay, so there's another concept of area of the black hole. So if you write this is for a spinning black hole. So I showed you the metric for a non-spinning black hole. This is one for a spinning black hole. You can actually calculate the area of this metric, and that turns out to be dependent on the mass and spin, right? So that's given by this. And there's a relationship between area and entropy. We will discuss that next. But what it tells you is that if the area has to increase, that is, the entropy has to increase, then it implies that the mass is always greater than A, right? So A is the spin of the black hole. The spin reaches a maximal value as A reaches 1, that is a maximal, the spin reaches its maximum value. The horizon is not destroyed, because you'll find that m squared minus a squared is always greater than 0. So that's required for the black hole to be, still described by this metric. A very important paper by Hawking in 1970s was this paper on Hawking radiation, where he showed that black holes can indeed evaporate. So he made a sort of interesting proposal of taking a particle and an antiparticle. What happens is that there is an evaporation, that is that the black hole will radiate through this pair production, and then as it goes out, it takes away the mass of the system. So a photon can come out, give you particles, and then the system goes to a more lower energy state, and therefore the mass of the system decreases. And when you write down the equations for it, the first thing that was done is the concept that you take up, obviously the Planck's constant is involved. So you take the Planck's constant and you divide that by a length scale, or h over x, and that will give you the momentum, right? And therefore that sets the scale for you. Lambda is h by p, right? So that is so this h over p is gm by c squared, right? So that gm by c squared is the length. So you can get h by p by equating it to that, and h by p is then equated to wavelength. So this intriguing idea, and then you will have to divide by the thermal kT by c, take the velocity of, so kT by c is roughly your p, because Pc is a relativistic energy, right? So Pc is kT. So if you thermalize it, you get Pc equal to kT. So kT by c is your p. So you get h by p is hc by kT, and that should be a wavelength. And that wavelength, you can only think of one number that signifies the wavelength or the size of the system, and that is gm by c squared. So using this very curious concept of generating radiation in a thermal bath, of the entire black hole being a thermal bath, and equating the photons of this size, he came up with this idea. And then, of course, people worked out the quantum picture of this in his paper. He worked out the radiation field from these concepts. You have the Planck's constant, you have the Boltzmann's constant, speed of light, the gravitational constant, relating the mass and the temperature. So you can see this very remarkable equation of physics, which is relating thermodynamics, quantum mechanics, relativity in one shot. So then this gives you this very interesting temperature, where the temperature is 10 to the power of minus 7 Kelvin if the mass is that of the sun. And you know that the area goes as m squared, because m scales with the radius. So what does this lead to? So suppose you have the black body radiation, which goes as the area times t to the power of 4, then you will have m squared multiplied by t to the power of 4, which is 1 over m to the power of 4. So then the radiation, Hawking radiation will scale as 1 over m squared. So the more massive it is, less radiation energy will radiate. So it's counterintuitive in the sense that so Hawking power is r squared t to the power of 4 is m squared by m to the power of 4 goes as 1 over m squared. If it is less than 10 power 17 grams, then it would have evaporated by now, right? So that this rules out stars and galaxies, if as sources of Hawking radiation. You can find out the radiation rate by equating dm by dt to 1 over m squared, and then find out how long it takes for this to radiate. Right. So people are looking for gamma ray background, which could be evidence of primordial black hole radiation. So this is the same concept which I just described to you. So if you take the radiation from primordial black holes and you find out how long it takes. So it takes 10 power 10 years for 10 to the power 15 grams to evaporate. So, and it would radiate at 10 power 10 hertz. And then you would get about 100 MeV in the radiation, or the photon energy would be that much. And so if you look at gamma rays at 100 MeV, that is about 10 to the power minus 8 of the closure density of the universe. So about a fraction, 10 power 8 minus 8 fraction could be primordial black holes. This is sort of a limit on the size of primordial black holes. Okay, back to Kerr geometry. Then you can write the Kerr geometry in something called the Boyer-Lindquist coordinates. And so this is, there are some details about this metric where, rho squared is r squared plus a squared cos squared theta. And this delta is this r squared minus 2m r, and a is a spin. A is actually the maximum spin when a goes from -1 to 1. And so this metric is then used to solve various things around the black hole. What you can do is something that I've extensively done with one of my students, is to find out, at least to calculate orbits around these Kerr geometry, in Kerr geometry for these black holes. So what you can do is reduce it to the effective potential, write the effective potential, and actually calculate orbits using this equation 1, for instance. You are familiar with the Kepler potential. Kepler potential is just the first two terms. In the effective potential equation 2, you have minus m over r, and then here, of course, g equal to 1 in units where g equal to c equal to 1. So minus m over r is the gravitational part. Then L squared by 2r squared is your familiar angular momentum part. The other things you would not have seen in the usual course of classical mechanics. They depend on the spin and the energy. So there are sort of interesting things that come about in Kerr orbits. First of all, you will not see a term which is cubic in the effective potential, but that comes in for the case of general relativistic potentials, and especially the Schwarzschild and the Kerr. So when you want to write the Schwarzschild non-rotating, you can just put a equal to 0, right? Then you will get L squared by 2r squared, which is your familiar Kepler parts. The first two will be the familiar Kepler's part, and then if you have an ml by r cubed, which happens ml squared by r cubed for the Schwarzschild part. You get additional terms due to the spin of the black hole. And from here, you can see that the horizon goes from m to 2m, depending on whether if a is 0, then your horizon is m, right? And if a is equal to m, it's maximally spinning, horizon is m. If a is 0, then it goes to 2m, right? That's an interesting fact. And there's another thing called stationary orbits. Stationary orbits, stationary limit is where an observer cannot remain stationary. It's a limit of the radius to which an observer cannot be stationary. So and just outside the event horizon, right? For example, if I put a equal to 0, then I'll just get m out of this equation. Okay, there's an interesting thing over here that depends on writing this for, if you take a equals 1, then this is 0, then this is minus 1 to the 1/3. So you will get, this is written in a very curious way. I mean, you have to solve this using complex numbers, and then you'll get, because of these two factors, both these complex factors will get reduced. And I'll show you a plot of it anyway, how the stationary radius behaves. Another important thing is the innermost stable circular orbit. And these things are illustrated better in a figure. So you can find out that in the innermost stable orbit, there is a circular orbit which is stable, right? And there is an innermost, there's a point at which this stable circular orbit occupies the innermost radius, and that is of significance for dynamics around black holes. And the reason it's significant is that beyond the stable circular orbit, the particles will fall in. So that involves certain amount of algebra, which is given here. So here is the ISCO. So you see this blue line, that's the ISCO radius. And then this L over M is the angular momentum, which is also drawn as a function of spin. And then 1 over E. So this goes from something like from 0.03 to about 0.6% to 43%. And it tells you the fraction of energy which can be lost due to a particle falling in. So that's the amount of binding energy in the system that can be lost. So if you have a spin of minus, which is counter-rotating, you can lose 3%. If it is not rotating, the black hole is not rotating, then you can lose about 6%. And if its black hole is maximally rotating, then you can lose about 43%. So imagine that you have a system, and this is what I meant, right? From point 0, this is 5%, 0.3%, should be 0.3%. This is 6%. This is about 0.3%. And then it goes to 43% at the top. And you can see how this is a very important curve, because thermodynamical or engines that you're familiar with in the universe, you can get, for example, a steam engine that can give you 10 to 15% max of energy conversion, right? Of energy in the steam to locomotion. Petrol and burning petrol, chemical energy is also of that order. So the efficiency involved in most systems are very, very small. It's even less in terms of rest mass energy. Nuclear fusion, for instance, is very efficient. The conversion of, fusing protons to helium, hydrogen to helium fusion that happens in the sun is about 0.007 or 7%. So 7% is, 0.7% is the rate of energy conversion of rest mass in the sun to heat. And that's the reason why the sun is shining and all of us are alive. And human life is possible because of this 0.7% of energy conversion. But the black holes are much more efficient. They can convert energies of the order of 3%, 6%, 43% if it's maximally rotating. So it's the most efficient energy conversion process in the universe. So these are different. Here's the orange. This curve is a stationary curve, which I told you. Inside the stationary yellow curve, you cannot remain stationary in front of a black hole. You have to fall in. You can be outside the stationary curve. You can stand on a rocket or have enough energy to keep yourself from falling in. For example, if you want to fall on Earth, you can just stand on a rocket and then prevent yourself from falling in, right? So you can do something to stay alive by outside the stationary curve, but inside that, if you're inside that, then you can't. So that's why it's called a stationary curve. So this is the stationary radius is a function of spin. Again, it goes from -1 to 1 spin. And so these are different curves. One is the innermost stable orbit, which is marked as 1. Then you have something called the innermost stable bound orbit. So it need not be circular, but it can be bound. So as long as you're not circular, you can be in the green curve. And then you can't remain stationary inside this. And then this blue thing is the horizon. So once you're inside the horizon, you can't come out. So between the horizon and the stationary curve, this region is called the ergosphere, and I'll show you what that is. So you can draw different. You can see it's a cubic potential. So effective potential is a cubic. So you can see different kinds of orbits that are possible. So here's an eccentric bound orbit, right? So there is a precession of this orbit that you can see. You see, if it were not for GR, then you will not have a precession of the orbit, unless there is a perturbation from outside, normal Newtonian mechanics. You will just have a regular elliptical orbit. So what are the orbits that Kepler, problem solves for? You can get hyperbolic, you can get a parabolic, or an elliptic orbit, or a circular is of course included in elliptic. But when you go to general relativistic system, then there is the orbit precesses around itself. So there is a pericenter, and you can see that the pericenter keeps, right, the closest point of approach makes a circle. That's the inner circle that you can see, and that is the precession of this orbit. So now we go to the ergosphere, right? So there is a 4-velocity stationary observer, and yes, and you can calculate the surface by putting u dot u equal to 0. I mean, let's not, I'll avoid these details. So I'll just show you pictorially what is an ergosphere. So this R plus and R minus, there are two radii, and these radii are the same if it's a non-spinning black hole. And even the ergosphere, everything is coincident. But moment I change the spin to 0.5, I find that the R plus goes in. The R minus is a smaller one that's inside the horizon. That is, R plus is effective horizon, and then this E is the region where you have the ergosphere, and this is in between the blue curve and the orange curve. I cannot remain stationary, right? So moment I enter the blue curve, I have to fall in. So these are the different curves drawn for different energies. So this is near the maximally spinning, the same diagram, but this is at 0.95 and 1, right? So you can see that the R plus coincides with R minus for A equal to 1. This is in the other set of coordinates. There's a rho coordinate and then the R coordinate. The Boyer-Lundquist coordinate and the actual coordinates are. Okay. So we looked at dynamics and the physical properties of the black hole from the geometric properties of the black hole. What does it mean for observations? What does it mean for people who are trying to look at radiation from black holes? How do you actually infer the existence of black holes? And a whole bunch of things. So observations is actually giving a puzzle for people to think about from various kinds. So how does the theoretician model all this? So there is this no-hair theorem which I told you, the mass, angular momentum, and charge. These are the only parameters that describe a black hole. But if you look at gas falling onto the black holes, then you have the mass, the accretion rate, the angular momentum rate, the luminosity of the jet, and then you have the magnetic field, and the spin. So these are the electrodynamical properties. And then you have stars surrounding the black holes, for which you can look at stellar density around black holes, the X-ray flashes which come out, which depends on time. So there are a whole lot of observations which are available and schemes to work out the different consequences and predictions for these observations. And you have to interlink them, as observations are also very so you have to sort of sort this puzzle of various observations and come out with a consistent theory of what describes the physics of these objects. So how do you determine the mass of the black hole? So there are several techniques. I'll just go one by one. One is if there's a water maser. So this is a paper, in I think close to 99, I believe, where you look at orbits of gas around the black hole, and then you can see this curve that follows a very nice, Keplerian curve. You know that v squared is 1 over r, so that's kind of curve that you get. And from this, you can measure the mass of the black hole by looking at the velocity. So this rotation curve shows the velocity of the water maser line. So you measure this velocity and then the distance, and then you can calculate the mass. So again, this very similar kind of approach is taken for stars. So you actually measure stars, you find the orbits of stars, and then from the orbits of stars, you can actually find the mass of the central black hole. There, of course, once to find the orbits and the velocity, you need to find the position and the velocity, and therefore then you would be able to solve for the mass using the same arguments. And then there is something called reverberation mapping. So this is also using the same idea of Gm by R equal to V squared, but the idea is that there would be a bunch of clouds, a broad line region. You measure the thickness of the line, the thickness of the broad line would give you the measurement of the velocity squared, and also the line width would give you the velocity, and using the velocity you can then estimate from the random motions you can estimate the mass. So again, same relation. So this kind of thing is useful and to measure the mass of the black hole. You can also measure the spin by using a little bit of more advanced theory, where you know that suppose there is an iron line which is at a very high temperature and therefore very close to the black hole. This line has a certain width. So once you know the width, you are able to go very close to the black hole. You can even probe the orbits around very close to the black hole. So once you probe orbits very close to the black hole, that would be a measure of the spin. So there's a detailed equation which tells you how the spin changes the orbit around the black hole, and that's useful to measure. Okay, so here's an idea which covers all these concepts. First one is the Newtonian picture. So if you have it's a double horn profile. So one horn is for let's take a ring that's rotating. So on the for the left part of the ring, you will find that there is a profile of the frequency which is related to the velocities. So the velocity coming towards you, there's one velocity that's coming away from you. So therefore, it's plus and minus. On both sides, you'll find this. So that is a Newtonian thing. And if it's special relativistic, that the motion is relativistic, then there would be a beaming effect. So there's a Doppler boosting of the photons coming towards you and Doppler deboosting of the photons going away from you. So this is coming towards you, this boosted, the other part is deboosted. So that's the transverse Doppler shift and beaming. Now there's a gravitational redshift. If you're coming from very close to the black hole, the photons get shifted in color. So that is the other part, the GR effect. So essentially, if you combine all of this, you will get the line profile that is drawn here. And this is what happens. And you can actually measure this and calculate the spin, the mass, and solve for the physical properties. So here's an example of how how one is actually going about doing this profile and measuring the spin and the mass and other properties of the black hole. Of course, the black hole not only has gas going around it, it has jets. So one of the things of studying jets is to find these connected to the magnetic field that's said to be producing the jets. So one is saying that there's a magnetic field, and the magnetic field in a spinning black hole produces a Faraday effect, and the Faraday effect produces an EMF, and the EMF drives a current, and that current produces the pointing flux, right? And that pointing flux is what the energy is, right? So the luminosity of the jet is from the pointing flux, and that pointing flux is a result of the magnetic field, and which is producing an EMF, and so you have a E cross B and a pointing. So here is a disk. You have magnetic field lines like this, and the black hole rotation energy is extracted and gets into the electromagnetic flux coming from the jet. So here is a current picture, a circuit picture of the same thing. So there is a load resistance, there is a spinning surface, there is a current that is developed because of the Faraday effect, and then you will basically deposit the current into this load, and therefore you will have electromagnetic energy extracted from the rotational energy of the black hole. Okay, I just told you a few things, and there is this diagram which I drew round about the time when I was, giving a talk on the Nobel Prize 2020. So there are several things which have cropped up. As I said, black holes are a new sea. Black holes are a new sea topic, and a lot of interesting things are coming out of black holes in the last decade or so, right? So you can see that the gravitational wave radiation that was given the Nobel Prize, the stellar orbits was given the prize, and singularity theorem was also shared, right? So one expects that the black hole shadow will also get the prize this soon enough, okay? And so there's the inner part and then there's the outer part. So the inner part involves the singularity theorem, cosmic censorship hypothesis, which tells you that it's impossible to form a singularity which is naked without a horizon. And then there's the Hawking radiation, Penrose process, entropy, and I told you just now about the electrodynamic nature of the black hole, and black hole oscillation, which are quasi-normal modes. There are other things that, from gas accreting onto black holes, you have observations which stretch from X-rays to optical to UV to, so these observations are continuously being done, right? And then there is the physics of gravitational, general relativistic MHD, and then there is relativistic jet, stellar dynamics around black holes. How stars get disrupted around black holes is another topic which is of interest to me. And then how do two black holes coalesce? What happens in the last parsec? That is when one small black hole coalesces with another black hole. What is the gravitational radiation that is given out? So all these are very interesting topics which is deserving attention of people working in it, black hole physicists, and because the reason is that they're becoming observable. So many of these things were pure fiction maybe decades ago, but they're now being able to observe and predict events based on the theoretical physics that was developed for this. So there are largely four kinds of metrics which are important. One is Schwarzschild, that is a spinless, chargeless black hole. And then there is a spinning, chargeless black hole, which is Kerr. And then the Rayner-Nordstrom, which is charged but not non-spinning black hole. And then the Kerr-Newman, which is both spinning and charged. So these are the four kinds of metrics. So this is sort of the landscape of black hole problems, which are there for you to look at. So there's the inside, which is heavily mathematical, and then there's the outside, which is a black hole astrophysics, which actually people can measure, people can observe, right? So things like black hole shadow, which is and stellar orbits, gravitational radiation. So these are entities which are actually observable, and they're so becoming more important to compute and compare. All right, so let me, I don't know how I'm doing on time. I've already spent probably 1 hour or more on this. All right, so this is one of the reasons, one of the parts of the Nobel Prize of 2020, right? And in short, this is about the concept of the cosmic censorship hypothesis. It says that every collapsing object will, beyond a certain point, will give you a singularity, and that singularity will be cloaked within a horizon. I'll explain this a little bit. This diagram is that once the space-time collapses to a point, and the point exists inside an event horizon, which you cannot see. Event horizon is beyond, you can't see inside that. That is the point. And the whole thing is that there are observers here who can see the part that, or the light cone that you see is yellow, which is called the future part. So you can see photons that are going out of the future part are connecting to observers. But at some point, the light cone turns towards the inner blue part, which is a singularity. So all the light rays are just going in. You cannot see it. So there's a trap surface, and the photons get trapped. So that's the point, that the singularity cannot be naked. Okay, the history of this goes back to 1939 to 1964, where people are trying to calculate a collapse of spherical cloud of matter. And the star tends to close itself off from any communication with a distant observer. So the key assumption here was spherical symmetry. Later on, Lifshitz and Kalatnikov tried to break this general case of arbitrary distribution and tried to say that even then it doesn't lead to an appearance of singularity. So later on, quasars were discovered. People suspected there were black holes of some kind, and how can you actually form, singular objects? Because a singular object is a result of Schwarzschild. So people knew the Schwarzschild result. So wanted to prove how you can actually form it. So Wheeler was the one who discussed this with Penrose first. And Penrose, this is the famous theorem in 1965, where he showed that the Einstein's energy expression is non-negative. So there is non-negative energy. So then he said that the Einstein's equations are, if the singularity is not permitted to occur, then there would be either the energy is negative, or the Einstein's equations don't hold, or the space-time is incomplete. So finally he came up with a topological proof of how there is a trapped surface that forms, that I showed you, and then how the light cones are actually trapped in that surface. So this is the schematic diagram of how the space gets converted to time, and then that forms a singularity through the event horizon. So this is the same picture where you see that the light cones are turned towards the singularity, and then the space gets converted to time, and then the photons don't reach the observer. This is the same diagram which can be converted to the form that is shown here. So you can make an infinite diagram, R and T going to infinity, by writing it as T minus R and T plus R, and taking a tan inverse of that, so that your infinities are converted to minus pi by 2 to plus pi by 2. And then there's a very neat diagram, you can study the collapse, right? This is Penrose's diagram. So, without getting into the various details, Penrose's result is regarded as the first post-Einsteinian result in general relativity. It proves that the gravitational collapse cannot be stopped after a trapped surface is formed. And once this is formed, then the density of the, even during its formation, it can happen in a stage when the density of matter is not high. And then it collapses to an infinite point. And point where all the mass goes to the center. So they extended this concept of singularities to the Big Bang. The Big Bang was also proved to be a singularity. So this triggered a huge, explosion in physics and astronomy, where people started looking at various concepts in and around black holes and the gravitational anomaly and all that. So the whole concept of black hole was first coined by Robert Dicke, and then Wheeler made it popular. So this is this concept of the cosmic censorship hypothesis, where you can't see a naked singularity, and there's a painting of which was used to make a cartoon, and the painting was done by Michelangelo, which is in one of the famous churches in Rome, and where the fig leaf is represented by the naked singularity, and then this is supposed to be Zeus, who is the cosmic censor. Anyway, it's a parody on the subject, which is a highly debated topic. There are people who still believe that you can form naked singularities. In any case, the supermassive black hole became the dominant model to explain quasars and luminous objects. Where do you get these luminous energies from? As I said, you can go from 4 to 6% to 43% of rest mass energy. So even if the objects are very, very far, as they are cosmologically at high redshifts, you are able to see them precisely because they are able to put out energies of 6 to 43%, right? So that is the level of the power that you can get from black holes. And that's why black holes are the most powerful objects in the universe. They're most visible, they're ubiquitous, they're found everywhere in the universe, and they can form from clusters of stars to from gas collapses and various other possible situations. Our own Milky Way has a galaxy, has a black hole in the center, and this black hole was measured for the orbits around this black hole. This is the second half of the prize in 2020. People measured painfully orbits followed the orbits of these stars for 25 years, right? They measured the velocities, constructed this very detailed diagram that you see on the right, several positions. So once you get the position and then you get the ellipse, then you're able to measure the mass of the black hole. And you know that the innermost orbit, S2, so there are different orbits, different stars, and they're telling you, that the mass of the black hole is contained within a certain region. So it kind of proves the existence of black holes. So this is the story about the Milky Way black holes. And there's a whole story of how different techniques were used to find it. So this is a speckle interferometric technique. As you know, the atmosphere blurs the images. So in order to avoid blurring, what you do is you shift and add them. You shift it and then you add them so that you get a clearer picture of what the original picture was. You take several exposures, shift and add, and then you can get the actual positions. By doing this, you can get actual positional motions of the stars. And once you do that, you can plot it as a function of distance from the center of the black hole. And then you see this 1 over v squared is equal to 1 over r. So v is proportional to 1 over square root of r. And you can see this nice relationship that comes out, which then gives you the mass, because v squared equal to gm by r, right? So you can see the dispersion and then calculate the mass. So here it clearly shows that the mass is 2.45 times 10 to the power of 6 solar masses. After this, another technique was developed called adaptive optics, So here what happens is that you have a deformable mirror, right? There's a laser guide star which is going through the Earth's atmosphere, and there's a turbulence in the atmosphere. The light front gets distorted, and then there is this distorted light front goes through the telescope. And when you're observing the actual star on the right, that also has a distorted wavefront. But to correct this distorted wavefront, you deform the mirror by programming. So you know how this to correct that image, you need to deform the mirror, and then you get a straight image that you can see on the right. So by using a guide star, and that guide star is some laser which is you shine laser light on the Earth, some part of the sodium atoms in the Earth's atmosphere, measure the reflection, look at and the deviations and the deformed wavefront. You correct the wavefront in the mirror, and then using a deformable mirror, and then you straighten it. So this is called adaptive optics. And using this, you can get a factor of 10, 20 times better resolutions, and so you can get beautiful orbits out of this system. And this is done again with the Keck telescope, and there are two groups that worked on it. One was a UCLA group, and there was another group based out of Germany, and the ESO, using the ESO, European telescope in Chile. Okay, the last bit I want to talk about is formation of black holes. I don't think I have the sufficient time, but I'll just say that black holes are formed from collapses, direct collapses, of a massive star, and then you can turn a massive star into a seed black hole, and then these stars can collect to grow into a single black hole, or you can take a single huge mass cloud and form a black hole. So we have done this calculation of taking a direct cloud of 10 to the power 6 to 8 solar masses at high redshifts, and then you collapse it, and then you cool it, and then you form a seed. So there are several detailed physics that happens here, and you can also form it through stellar clusters. You take a cluster of stars, and it collapses. And so this is in one of my papers. I've shown how a collapse factor you can get, of using radiation in the background. Another thing is, relativistic precession, which I talked about. These are oscillations of the orbit due to general relativity. Either the plane itself oscillates, or then you have the relativistic precession of the periastron, right? And there are various orbits. One is the interesting equatorial separatrix orbit, that you can see that the star comes from very far and then spins around in a circle. Or you can even get oscillations which you can be measured in X-rays. And there are stars which can fall in. So I think I'll skip all this. There are details of how stars can fall into black holes. They can be observed. So how you can study this, the useful laboratories for studying different kinds of physics. Stars getting disrupted in front of black holes. What is the light curve that comes out? What are the different ways you can study it observationally? You can get alerts in X-ray satellites. Various events happen from months to year to few years in radio, optical, UV. So there are various events that you can study. And of course, there is this famous thing about the shadow of the black hole, which I described. I'm looking at the theoretical aspects of this also. Now, in the future, you will have the 30-meter telescope coming in, so which is India is participating in, but there's some logistical problems with it. But this is a great laboratory for doing black hole physics. You can study the galactic center black hole, study the dynamical orbits around close by black holes, coevolution of black holes, time variability. So this is a short view of two scientists talking about something. It says it's black, it looks like a hole, so I'd say the black hole. I'll end up with questions that one can, at least from the talk and various subjects that I've covered, topics I've covered. How are black holes formed? How do we explain oscillations in black hole systems? How are jets created? What is the physics of the mass and the stellar dispersion relationship? What is the stellar feeding of rate of black holes? These are all some of the open questions. There are more questions to ponder about than I have time for. Thank you very much.
Sir.
Thank you, Professor Arun.
Welcome.
Thank you, sir, for such a wonderful talk. And we have so much information about black holes. Okay, I'll read all of the questions because there is many questions in the chat box. So I
Yeah.
will read one by one. Okay, Rishi asked, is it
Okay, let me
ergosphere?
start from the top. There is Aditi Giri who has asked, what is the m dot symbol? Okay, m
Yeah,
dot is the
sure.
mass rate of dm by dt, which is the increase of mass with respect to time. Okay.
And after that,
What is, did I say m with dot on top or m circle dot? Which one are you asking? M circle dot with as a subscript is the mass of the sun. Okay, so I don't know. There are two symbols. I'll just show you one of them. For example, I don't know where it is. Any one of them will have these symbols. Yeah, this is m dot, which has to dot on top of m. That is a dm by dt, and yeah, you see this m circle dot. That is mass of the sun. Okay, any other question? Let's see.
Yeah, Rishi asked that, is it ergosphere?
Okay, which is ergosphere? I don't know which. Ergosphere is the one which I drew. Okay, one sec, hold on. So you can see that for the spin equal to 0, they're all coincident. And there is this blue line and the yellow line, right? Now the blue line is the edge of the ergosphere. Blue line and the yellow line are the edge of the ergosphere, right? So R plus is the ergosphere is this blue line here, right? So beyond which you cannot remain stationary. So that is called the ergosphere. And in between, the energy of the particles can be extracted. Okay, next question.
Okay, okay, sir. One of the question is that how to measure the charge of a black hole?
Okay, so charge of a black hole, actually, any charged black hole gets shorted out because opposite charges will collect. So that's a very difficult thing to measure. But as I said, there is this metric which I showed you, the general metric for a spinning charged black hole. So if you look at the orbits around this black hole, you can find out its motion, and then you can fit it. It will not necessarily be one of the orbits of a regular Kerr black hole. It will be having some other different dynamics. So from the dynamics, one can measure. Okay, one more.
Okay.
Ambika Govind, what is her question? Hope it's not too off topic. What is that? What is her question? Ambika?
My question is further down in the chat window, sir.
Okay, it's further down, is it? Okay, let me see. Okay, when the star is in the main sequence phase, as well as during the supernova, it must definitely have lost some mass. So the gas left after the explosion equal what was there in the nebula and what prevents nebulae from forming back in the first place. Okay, so you're confusing several concepts here. In fact, you've got the entire stellar evolution written in one paragraph. But the star is in its main sequence. Once it's in the main sequence, nothing happens to it. No, it's just burning hydrogen. But once the hydrogen is exhausted, then it goes off the main sequence. It's burning helium, then it burns higher elements, atomic number elements. At some point, when the burning stops, right, all the fuel is exhausted, then the stars begin to collapse, right? It cannot support itself. The nuclear fusion stops and then it starts collapsing itself. Once it collapses, then it becomes a white dwarf, right? And if it collapses further, then it becomes a neutron star, and then that explosion leaves a nebula. So what is your question? If the mass is higher than a certain limit, I think I've explained this in one of my first few slides.
Sir, what I'm trying to say is that the mass of gas from which was present in the nebula initially has to be greater, if not equal to the mass that is left after the supernova explosion. Is that correct?
Okay, I think I have the answer in this one of these slides. Okay, see, the end product of stellar evolution. A neutron star has to have a progenitor. It's called a progenitor. What mass that started off with. So the progenitor of a neutron star, which could be of a few solar masses, will be about 8 to 10 solar masses. Which means about, if you take a 10 solar mass star, 7 solar mass star will be blown off. About 3 solar mass star will remain, right? And a white dwarf, which is only maximum 1.5 solar masses, will have, of course, it depends on what kind of a white dwarf it is, but typically 1.5 solar masses. You would have to start with some 8 solar masses. So the planetary nebulae will consume about 70% or 80% of the gas of the shell. The shell part will be about 70 to 80%. Remaining will be in the star. I hope I answered your question. And similarly for black holes, a majority of once the black hole is formed, uh, majority of it is lost in the supernovae. Okay, let's go back now. Mayuk, how do you? I've answered that. Then what is a tidal disruption event? A tidal disruption event is a star being, maybe it's in one of the slides. I don't know why. Okay. Here it is. So you see this picture of a star being broken up, right? So in front of the star, it's closer to the black hole. So the gravity in front of the star is more than the gravity behind the star, right? Because gm by r squared is a force, and this r is a little further away on the back side of the star, and the front side of the star, the r is different. So that's the tidal force. So it's enough to tear the star apart if you're very close enough to the black hole, and that's going as 1 over r cubed. So that is tidal stretching. Okay. Saurabh Sharma has asked, how can we say the black hole is spinning or not? I showed you the iron line, right? So that is how you measure the spin of the black hole. One of the ways. Okay. Then, so the dynamics will tell you, the orbital dynamics will tell you that the orbit is how the black hole, whether the black hole is spinning or not, because the space-time changes. Once the space-time changes, then the orbit changes. So from the orbit, the velocity, the breadth, the width of the line, of the emission line will change. So can a black hole break into 2 black holes, naturally or forcibly? No, the reverse can occur. Once you form the event horizon, you cannot come out of it. So in a sense that you can coalesce 2 black holes to form a black hole, but the other process is not possible. It's irreversible. When a star is in main sequence as well as, okay, this is the first question. Mohammed, electric charge is one of the 3 characteristics of black hole. What does it mean for electric? Okay. Well, it's just like an object which has mass and charge, correct? So it has dynamical consequences, it has electrodynamical consequences, mechanical consequences of having a charge, right? So Maxwell's equations will hold in some relativistic form. So there are some things known as the Einstein-Maxwell's equations. So they govern the dynamics of such objects. Okay, then are there any theories for formation of black holes other than quasi-stars? I think I skipped this part. I sort of rushed through the formation of black holes. So, see, there are many ways of forming black holes, right? One of them is to start with a huge gas cloud, and this is one of the things I have worked on. And then that huge gas cloud will collapse. Okay, so what came first, galaxies or the central black holes. And then how did the black holes form at high redshifts? So because you need black holes already formed at very high redshift, that is very early in the universe. So you explain two factors. So either they form from heavy stars and then you collapse all these stars together and form them, or you take very small black holes and keep on adding gas to it. That is one way. And then there is a direct collapse of heavy gas clouds. So these are roughly three ways. And then this collapse of star clusters, you form stars and the many stars collect together and form black holes. So it's a little bit of confused subject right now. And there are two methods which I have worked on. One is that you use stars and then you collapse stars to form million solar masses, then you collapse million solar mass black holes into a large supermassive black hole. Okay, any other questions?
So last question maybe.
Yeah, are there any theory for formation of black holes other than quasi stars? What is this R plus? R plus and R minus are two horizons of the black hole. You mean there's the ergosphere radius and R plus and R minus? What is that got to do with formation of black holes? Once a black hole is formed, you will have the ergosphere if it's rotating, and an R plus and an R. These are all for a Kerr black hole. They're all equal to the same thing if it is a non-rotating black hole. So to form a rotating black hole, once you form this, these are entities which are associated with the rotating black hole.
I just wanted to clarify that for the previous question that I asked, is this the ergosphere? I meant, I just wanted to write this because I wanted to know this. This is not related to the last question.
Ergo means in Greek, it means energy, right? So ergosphere is where energy can be extracted. So that means that inside this region, the sphere, the rotation of the black hole, that energy of rotation of the black hole can be extracted, right? So that's what it means. So that is the RE, where it also coincides with the stationarity radius, where you cannot remain stationary with respect to the black hole. You have to fall in.
Okay. So that's all. Sir, I have one question that I have read that from a charged black hole we can get out from that. So is it possible?
Yeah, no, it's not exactly that, but it's something called a white hole. So the white hole is where you can come out. So you can. That's like saying that it's the other end of a black. So if you connect two black holes, one is your space-time is connected to the space-time of another universe, right? So there is this concept of a white hole and all that. But people can create those objects mathematically, but whether they exist in reality is a big issue.
Okay. And another question that event horizon of the black hole is a light-like region is black. That event horizon region, because light-like means it's around the light is traveling around.
Yeah, see, the event horizon signifies the point at which, it's a point of no return, in the sense that once you go inside, you can't come out. Any particle and the time signal itself stops there. So, you cannot get any signal from inside that region. It's cut off. Communication is cut off from that part. So it's a boundary, your edge of communication. If you stand in front of the black hole, you can shoot photons only to people outside the black hole. So you cannot communicate to people inside or to entities inside the black hole. That is the point. So it's a horizon of communication, either light signals or anything.
Okay. One other thing that I am curious that how do black hole interiors actually grows up? And
how do black hole? Say that again.
Black hole interiors. Why do black hole interior grows?
Okay, that's the M dot. That was the first question. M dot, because the mass falls in, mass increases with time. So you're allowed to fall in and increase the mass of the black hole, right?
That means it's accreting the matter from the secondary star.
Yes. You can accrete matter. You can dump angular momentum. You can do lots of things with it, and you can also evaporate the black holes. That's the other thing. Even as slowly as possible, but it's possible to evaporate black holes.
So let's say two black hole is collapsing each other. That two. So area will be the conserved. That means the total area of two black hole will be the resulting black hole. Yes. What will be the dependent term?
Yeah, as I told you that the entropy, right, is synonymous with area of the black hole. So the area will keep on increasing. So once you take two black holes, let's take M1 and M2, and you add them together to form a single black hole, you will find that the area of that collapsed object has increased. So that is what it means.
Okay. So at the end of the life of the black hole, so what will last happen? That Hawking radiation will happen. This sort of thing. That
Yeah,
what will be the
eventually,
end of the life?
if you wait long enough, then the black holes will also evaporate. But that time scale is just enormous, right? So
Yeah.
yeah, and effectively, if you just let a black hole rotate in vacuum, then nothing happens to it. Okay.
Okay. Okay. Thank you.
Okay, guys. Thanks a lot. I don't know if there are any other. And
Yeah.
thank you.
Yeah. Thank you very much.
Yeah.
So, okay. So, anyone else have any questions for Professor Arun? You can ask. You can unmute and ask. It's the last chance. Okay. So, if not, let's thanks Professor Arun, and then it's a very nice evening with you and lots of information. I think our students have
Yeah.
really.
I apologize for sort of if the lecture was not too clear or lack of clarity and lack of too much of information or too less. I don't know what the complaint may be. There are usually a lot of complaints when at this level, because it's difficult to teach a subject at an introductory level, but having some useful information to the large public. So it's a difficult challenge, but hopefully I've done some justice to it. And I
Yeah.
apologize if you didn't find it very interesting or didn't find it clear enough. But thanks a lot. Nice to meet you, and
Yeah.
hopefully, we'll our paths will cross again.
Yeah. Sure. Definitely. Thank you very much. Okay.
Okay, bye bye.
Thank you, sir.
Bye bye. Bye bye.
Right.